Hello, everybody, and welcome to episode 4.1. This is part one of a two-part series that will introduce transshipment problems, also known as distribution or transportation network problems. In this episode, we will cover the basics of transshipment problems with a simple example, and in episode 4.2, we will expand on this topic by introducing a capacitated transshipment problem over multiple periods and with inventory carry. Before we get started, please don't forget to hit the subscribe button below. Let's start with a quick overview of what a transshipment problem is. Transshipment problems are network optimization problems, typically dealing with supply chain distribution or transportation. As depicted to the right, products or materials originating from a variety of starting points must traverse through a network of routes to intermediate nodes or waypoints, and from there move on to a final destination. This type of transportation problem is characterized by the existence of intermediate transfer points. In these problems, there can be one or more layers of intermediate transfer points or waypoints. To illustrate this concept, we will solve an adapted problem from an Introduction to Management Science, a quantitative approach by David R. Anderson. As usual, let's start with the problem description. RMC Incorporated consists of 3 plants. Each of these plants sends its product to 2 warehouses, A and B. From these warehouses, it then supplies 4 customers. Each plant has a given capacity to supply product. The cost to move product from a plant to a warehouse and from a warehouse to a customer varies by route. RMC Incorporated would like to determine the most cost-effective way for supplying all 4 customers with its product. As you can see from the depiction below, there's a variety of routes that exist from each of the 3 plants to the 2 warehouses, and from the 2 warehouses to the 4 customers. Let's move on to the problem definition. We know that the plant capacities for plants 1, 2, and 3 are 450 units per week, 600 units per week, and 380 units per week, respectively. We know that shipping costs vary among the plant to warehouse and warehouse to customer routes. We know that weekly demand varies among the 4 customers, Scion, Omega, Epsilon, and Apex. We're only considering a single period for this problem. And we know that inventory must remain balanced at each warehouse. That is, we cannot build or draw inventory at either warehouse A or B. Our opportunity statement is to determine the amount of product to ship from each plant and along which routes to ship that product so that shipping costs are minimized and all customer demand is met. With a well-formulated problem and a clear objective, let's move on to model development. We will start by specifying the various parameters needed in our model. We're going to let the numbers 1, 2, and 3 represent plants 1, plant 2, and plant 3, respectively. We're going to let letters A and B represent warehouse A and warehouse B. We're going to let letters S, O, E, and X represent Scion, Omega, Epsilon, and Apex, our 4 customers. We're going to let lowercase p represent the set of plants we have, plants 1, 2, and 3. Lowercase w represent the set of warehouses we have, warehouses A and B. And lowercase c represent the set of customers that we have, S, O, E, and X. M sub p is going to be the capacity of plant P to supply product. D sub c is going to represent the demand for customer C. FW sub PW, which is short for freight to warehouse, is going to represent the cost to ship product from plant P to warehouse W. FC sub WC, which is short for freight to customer, is going to represent cost to ship product from warehouse W to customer C. SW sub PW is going to represent the amount of product shipped from plant P to warehouse W. And SCWC is going to represent the amount of product shipped from warehouse W to customer C. Our objective function has 2 terms. The first term represents the total cost of shipping product from our plants to our warehouses, and the second term represents the total cost of shipping products from our warehouses to our customers. Combined, this represents the total cost for shipping our products to the customer. And this objective function is going to be minimized by our solver. For the left-hand term, we have SW sub PW, which again is the amount of product shipped between plant P and warehouse W multiplied by the freight to warehouse cost, FW sub PW, between plant P and warehouse W. And we sum that product up across all warehouses and plants. For the second term, we have SC sub WC, which is the amount of product shipped to each customer from warehouse W to customer C, multiplied by the freight to customer, FC sub WC, which is again the cost to ship from warehouse W to customer C. That product is summed up across all customers and all warehouses to give us our total cost. Our decision variables are SW sub PW, again, the amount of product shipped from plant P to warehouse W, and SCWC, which is the amount of product shipped from warehouse W to customer C. We have a total of 5 constraints. These 2 constraints at the bottom represent the lower bounds on our decision variables. So the amount of product we're shipping between each plant and warehouse and each and each customer. And for each of those decision variables, they have to be greater than or equal to 0. The other 3 constraints represent a constraint on our plant capacity, our warehouse inventory balance, and our customer demand. For the plant balance or plant capacity, we know that the amount of product we ship from plant P to W, which is SW sub PW, summed up for all warehouses, has to be less than or equal to M sub P for a given plant, the capacity. And we do that for each of our plants. For our warehouse balance constraint, we know that the total amount of product going from all plants into a given warehouse, which is SW sub PW summed up for all plants, has to be equal to the amount of product leaving a given warehouse to all 4 customers, which is represented as SC sub WC summed up across all customers. Therefore, this left-hand term minus this right-hand term has to balance and be equal to 0. And we do that for each of our warehouses. For the customer demand, we have the total amount of product shipped between our warehouse W and our given customer C, summed up for all warehouses, has to be equal to the total demand for that customer, which is D sub C, and we do that for each of our customers. So with our mathematical model formulated, we're now ready to move on and see how to code this in Python. As usual, let's start with importing the necessary libraries. That includes pandas, numpy, and pulp. Pandas deals with data frames, numpy with numeric operations or mathematical operations, and pulp is what we use to construct our mathematical model in Python. After we've imported our libraries, the next step is to read in our data. So we're going to go ahead and read that in, and then I'm going to pivot over to the Excel data file to go over our actual data. For our data file, we have 4 tables. We have a plant shipping table, a plant table, a customer shipping table, and a demand table. The plant shipping table has our plant warehouse pairs. So for each plant, 1, 2, and 3, we have a pair of warehouses A and B. And for each of those pairings or combinations, we have a given cost to ship product from that plant to that warehouse. So for example, shipping product from plant 1 to warehouse A is $4, while shipping product from plant 3 to warehouse B is $6. As you can see, we have a fairly non-uniform shipping rate between each of these pairs. With this exception here, the rate to ship from plant 2 to warehouse B and plant 3 to warehouse A is the same. Our plant table is very simple. It has each of our plants and then their product supply capacities. Again, these are in units per week. So 450 units per week for plant 1, 600 units per week for plant 2, and 380 units per week for plant 3. Our customer shipping table has the shipping rates by customer warehouse pair. So for each customer, Cyan, Omega, Epsilon, and Apex, there's a route that exists from each warehouse A and B. And for each of those routes from warehouse A or B to the customer, we have a shipping rate. And again, as you can see here, it varies amongst all the routes, with a couple routes having the same value. And finally, we have our demand table, which is, again, just a listing of our 4 customers and the demand for the products. So you can see for Cyan, Omega, and Epsilon, each of those customers has the same demand level of product, which is 300 units per week. And Apex has a slightly higher demand at 400 units per week. So now we'll pivot back to the Jupyter Lab notebook and go forward with solving this problem. Now that we are back in the Jupyter Lab notebook, we can quickly check each of these tables was read incorrectly. And as we can see down here, everything looks appropriate. So now we can move on to defining our input parameters and variables for the model. To start, I'm going to go ahead and just create 3 unique lists for the plants, the warehouses, and the customers. I'm going to use these to create data dictionaries for the various parameters that I'll need in my model, as well as the decision variables. I'm going to start with our first parameter, M sub P, which again is the maximum capacity to supply product for a given plant P. And I create this by looping through each record in the DF plant table, and then based on the key, which again is the plant, assigning the appropriate capacity. I do the same thing for D sub C, which is for our customer demand. I'm going to loop through each record or row in the DF demand table. And for each of the customer keys, I'm going to assign their appropriate demand level. And then I have 2 nested dictionaries for FW and FC, which again this is the freight to warehouse, or the cost to ship from a given plant to a given warehouse. And FC, which again is the freight to customer, or the cost to ship from a given warehouse to a given customer. And the primary key for FW is going to be plant. The secondary key will be warehouse. And then for each of those keys, I'm going to assign a shipping cost. And similarly for FC, I'll have a primary key, which is the warehouse, and a secondary key, which is the customer. And then for each of those key pairs, I will have a shipping cost. So once I construct and build these, I can go ahead and make sure they all were built correctly. And we can see here everything looked good. For M sub P, I have M sub 1 at 450, M sub 2 at 600, and M sub 3 at 380. All those are the correct capacities for plants 1, 2, and 3. Similarly, I have D sub C, so I have D sub Scion, D sub Omega, D sub Epsilon, D sub Apex, where I have the correct capacity of 300, 300, 300, and 400. And then finally, I have FW and FC, which are my nested dictionaries. The primary key is plants 1, 2, and 3, and then the secondary keys for warehouses A and B, and the appropriate shipping costs. And I also have for the other one, FC, my warehouses as the primary key, and my customers as a secondary key with the appropriate shipping costs. So with that, I'm ready to move on and do the model construction using pulp. Step 1 is to declare our model object, or create our model object. We use the pulp.lp problem syntax, and our first specification is to name the problem, which we're going to name it as transshipment problem. And second is to tell pulp what kind of problem we're trying to solve, whether it's maximization or minimization. And here we use the pulp.lp minimize syntax to create a minimization problem, and we assign that to our model object. In step 2, we're going to create our decision variables. I make 2 nested loops here. Nested lists. These nested lists contain all of our plant warehouse pairs and warehouse customers pairs. So for the plant index, it's a list of our plant and warehouse routes. And for the customer index, it's a list of all our warehouse customer routes. And we're going to use these to create our decision variables SW and SC, which again represent the amount of product being shipped from the plant to a given warehouse and from a given warehouse to a given customer. So for SW, we use the pulp.lp variable.dicts syntax. We're going to give the prefix of our decision variable name SW, and then a suffix of PW for PW in our plant index. Again, we have a non-negative constraint on these decision variables, so the lower bound is set to 0. And even though we should technically be looking at units as integers, we're going to use continuous because that does help us out with the sensitivity analysis piece. And for a final solution, we can always round these continuous results to the nearest whole number. And then similarly for SC, we're going to do the same thing, exception being we're going to use the customer index to create the right subscripts for SC. And then we can check to make sure that the decision variables were built correctly. So we see here SW, we got SW1A, SW1B, SW2A, 2B, so on and so forth. So those decision variables are correctly built. And for SC, we see something similar. We see SC A Scion, SC B Scion, so on and so forth for each warehouse customer pair. The next step is step 3, which is to create and add our objective function. So we're going to start by just creating an objective function, and then we're going to add those two terms we discussed earlier to it. The first term, which is the cost for shipping product from the plant to the warehouse, which is SW sub PW times FW sub PW, and we're going to sum that up for all product warehouse pairs or routes in plant index. Similarly, for the second term, which again is the cost for shipping our product from the warehouse to the customer, we have SC sub WC multiplied by FC sub WC or WC and the customer index. And we sum, and so we take those two terms and we add them to the objective function. And once we have that objective function created, we add it to the model. And that step 4 is to add our constraints. So just very quickly, we won't create the non-negative constraints here because we already specified those in the lower bound of the decision variable. So we'll only focus on the 3 constraints for plant balance or plant capacity, warehouse balance, and customer demand. For the plant balance, it's pretty straightforward. So for each P in plant, so for each plant, we want to sum up the total amount of product being shipped from that plant to a given warehouse. So SW, so PW, we're going to sum that up for all warehouses. So for all the products shipping from plant P to each warehouse, the total sum of that has to be less than or equal to M sub P, which is the maximum capacity of that plant. And then we just name this constraint as plant balance underscore P, which is the plant, whether that's 1, 2, or 3. Again, we'll create that for each of our plants. Similarly, for the warehouse balance, we're going to say for W in warehouse, so for each of our warehouses, we need to make sure that we have the same amount of product being shipped in as we do being shipped out. So we look at SW sub PW, which is the amount of product being shipped to warehouse W from plant P, and we sum that up for all P in plants. And then that has to be equal to the total amount of product being shipped out of that warehouse, or SC sub WC, and we sum that up for all customers getting product from a given warehouse. And we're going to do this for each warehouse, and this has to be equal to 0, and then we name it warehouse balance underscore W. For customer demand, we're going to go for each C in customer, the total amount of products being shipped across all warehouses to a given customer, or SC sub WC for W warehouses, summing that all up, has to be equal to D sub C, which is the total demand from customer C. And we name that demand underscore C. So we can create all of our constraints here. So we have created our model object, named and defined the type of problem that we're going to solve, created our decision variables, built our objective function and added it to our model object. And we have also now created all of our constraints and added those to the model object. So the next step here is to solve this model. Again, if you've seen previous videos, we are using the default solver, which is CBC. So we're gonna go ahead and write the model first, take a quick peek to make sure that everything looks correct and that it was built as intended, and then solve it down here. So we write the model using the .write_lp syntax from pulp. And we can come in here and we can look at it and make sure everything looks correct. So for objective function, we've got our SC and SW decision variables, right, multiplied by the respective cost to ship from warehouse A to customer Apex. So that's correct. So for each of these decision variables, if we decide to ship anything on these routes, it'll get multiplied by the respective shipping cost. And this all added together will be our total cost. And you can see that we are going to minimize that. Subject to these constraints, so we have our demand constraints for each customer. We have 4 of these, and this looks correct. So for each warehouse A and B going to this customer, the total sum of these decisions has to be 400. And we see that recreated for each customer correctly. And the plant balance and warehouse balance also look correct. We have SW1A and SW1B, which is again the amount of product shipping from plant 1 to warehouse A and plant 1 to warehouse B. And the total sum of those has to be less than or equal to 450 units per week, which is the maximum capacity to supply product for plant 1. We see that recreated for plants 2 and 3. And then for the warehouse balance, we see something similar. So this all looks correct. So now that that's done, we can go ahead and solve this problem, and which I've already done, and we get an optimal result, which is always a good sign. And we now can look at the objective value function. So we see that for our solution, our optimal solution, we have a total cost of $11,850. So that is what it will cost us to supply all of our customers this week. And the next thing we want to do is actually go through and look at the results. So what I'm doing here, and I'm not going to walk through all the details of this code, but I'm basically creating an empty data frame for all my variable classes. And I'm creating columns for each of the different indices that we used in our model. So plant, warehouse, customer, and then I'm going to have the name of those decision variables and also the type, whether it's shipping to the customer or shipping to the warehouse. I'm going to build this, and then once this empty data frame is made, you'll see this down here. It'll look like this. I'll be able then to add to this data frame the actual results that we got when we ran the solver. So again, just as an example, we have SW, which is our decision variable for shipping product from plant 1 to warehouse A. So we've got plant 1, warehouse A. Obviously, there's no customer in this decision variable, so that's a null field, and it is a SW type decision variable. We only have 2 types in this model, so the other ones down here are SC, which are the shipping to the customers from the warehouse. We see null field, no values for the plant, but we see the warehouse and customer fields complete. Next is to add to this, we're going to actually loop through here. So we're going to go through, we create some empty lists just for storing values, and then we're going to add them to the data frame. But we basically use this piece of code here, which is a loop. We're going to go through each J or each element in model.variables. So for each of the variables in model.variables, we're going to append values to these lists. So the class of the element is a variable. We're going to append J, which is actually going to be the name of the decision variable. Then we're going to append J.var value, which is actually the result from the solver for that decision variable. So i.e. how much we're shipping, whether it's from the plant to the warehouse or the warehouse to the customer. And then the reduced cost. So if we did not ship anything on the route, whether it's from the warehouse to the customer or the plant to the warehouse, we'll get the reduced cost, which would be a reflection of how much that shipping cost for that route would need to be modified by in order for the model to want to choose that route. And we're going to take all of these lists, do some basic formatting and rounding just to get some clean looking numbers. And then we're going to actually merge that with this data frame. And the result is this. We have our decision variable data frame here. And if you've seen the previous episodes, we're setting it up this way because if you are going to use like any sort of business insights or data visualization tools for a more complex model, this will make that a lot easier. But we can see all of our decision variables here. We can see their values, whether we shipped anything on those routes or not, and the reduced cost. So for example, up here we have our ship to warehouse. So we can see that from plant 1, we shipped 450 units to warehouse A, but we did not ship any units to warehouse B. And we can see the reduced cost for that route of plant 1 to warehouse B is 3. So that means we would have to reduce the freight to warehouse, or the cost to ship from plant 1 to warehouse B, by 3. Unit of 3, it's $3 per unit, in order for the model to choose this route over this route, or for at least plant 1. And then we see similar patterns for plant 2. It prefers plant 2 to warehouse B over A. So it sends 600 units there. And then for plant B, we're sending 250 units from plant B to warehouse A and none from plant 3 to warehouse B. And actually what you can see here is that you can see 450, 600, and 250. So if we go back and compare the capacities of these plants, what we end up seeing up here is 450, 600, and 380. So we're using all the capacity for plants 1 and 2, but we are not using all of plants 3 capacity. And since this is a simple example, we can kind of see why, but on average, we see that for plant 3 to ship to warehouse A or warehouse B, it's on average more expensive. So for warehouse 2, which is a higher capacity, to ship to warehouse B, that's cheaper than plant 3 shipping to warehouse B. And for plant 1, shipping to warehouse 4, we see that, warehouse A, just $4 per unit. That's much cheaper than plant 3 shipping to warehouse A. So, intuitively, this kind of makes sense on its face. But we can see that more clearly down there with these reduced costs. And then for the customer, for the SC variables for shipping from warehouse to customer, we see that we're supplying Scion from warehouse B, Omega from warehouse A, Epsilon from warehouse B, and Apex from warehouse A. And again, reduce costs. So if we wanted to supply these customers from a different warehouse, we would have to reduce those shipment costs by the reduced cost value in order for those to be competitive with the other decision routes. And then we can look at our constraints. So as you know, we have the 3 classes of constraints: our plant balance, our plant capacity, our warehouse balance, and our demand. So we can see that for our plant balances, we see that plant 1 has no slack, plant 2 has no slack, meaning we're using all the capacity of those plants. And for plant 1, we do have a dual value or a limit cost of -1. So what this means is that if we were to increase the capacity of plant 1 to supply product by 1 additional unit, it would improve our objective function by -1. So it would lower the overall cost by $1. And then for plant 3, we have quite a bit of slack, 130 units per week. So no dual value there. And plant 2, even though it is constrained and there is no slack, the model prefers to unconstrained plant 1. For our warehouses, we have a fixed balance, so the slack is 0. These dual values are meaningful in terms of this warehouse balance, but not really in the context of this problem because we're just forcing the balance to 0. And then finally, for our demand constraints, all of our demand constraints are met, and you can see these dual values here basically saying, hey, this is what incremental demand would be valued at. So if Scion, Omega, Epsilon, or Apex were to increase their demand beyond these values here, it'd be worth $8, $9, $12, and $9 respectively. So this is a basic introduction to transshipment problem. And that's it for today. So thanks for tuning in, and we'll see you next time.